times f. Any questions up to here? All right. So I'm going to write down, we'll work an example. It's one that you should be familiar with. So we're going to let xa, xb equal to the interval 0 to L. We're going to have our bar with a load P. It has cross-sectional area A and Young's modulus E. It has length L. We're going to use one element rather. Okay. So in this problem, now we all know what from undergraduate mechanics, what's the, and we already talked about it in this class too, what's the end-tip displacement for this problem? PL over AE, right? PL over AE. So that's the exact solution to the differential equation, right? So in this problem, then Kij is going to go from 0 to L. Well, let me just identify it this way. In this problem, using our model equation that we've been working with, if we let C equal to 0 and A equal to AE, then we get this K, Kij, is equal to like that. Okay, let's see if I can work this in Mathematica. I don't have any notes, so I'm doing it live. And sometimes that gets me into trouble. Okay, so I'm going to take this piece of the code here, put it here. So just for reference, this is the shape functions we're using, okay? What we're going to do is we will, again, 1, 1. Okay, so there's our shape functions. Yep. Blow it up? Yeah, sorry. Better? Okay, so there's our two shape functions for this problem. All right. We need to make our shape function matrix. So we'll do K is equal to the integral from 0 to L d n x, right, times d n x. Should be actually, sorry, let me start over. From 0 to L EA D n x times D n x. Okay, now dx. Now, remember, if I take this, right, this is a list or a vector, however you want to think of it. And so if I just do d n x, this will be 1 over L, right? But then if I just multiply those two things together, it's just going to do an element-wise multiplication. That's not what I want, right? What I need to do is put my i's and j's in there, right? So the way you do that in Mathematica, the syntax is like this: I, j, and then what I want to do is create a table, or multi-dimensional table, which is a matrix, where I goes from 1 to 2, and j, actually, to automate it for the future, I'm going to say goes from 1 to the length of n, and j goes from 1 to the length of n. Okay? Oop. Okay? So that is my K matrix. This is also known as the stiffness matrix. Even in problems where, say we're solving a mass balance equation, we still call it a stiffness matrix. And it's just legacy. Originally finite elements was kind of formulated in a kind of a matrix methods and structural mechanics way. And so that the stiffness matrix meant the stiffness of the system, right? But we still call it that even if we're solving a different problem. But that's our stiffness matrix. So let's just briefly go back to our notes. So if we write that down, we have A E over L minus A E over L minus A E over L, A E over L times the unknown displacements, U1 and U2, and that's equal to, and so in this problem our QI is P, and it's actually Q2, right? Q2 is P, the force applied to the second node is 2, okay? And so that's, then the right-hand side would be 0 and P. Okay? So now we have a system of equations we can solve. Maybe. Now, before I write the system of equations, I want to check something. I want to check the determinant of K. What does that mean?
Singular matrix.
What does that mean?
Cannot invert the inverse. Cannot invert.
Can't invert it. So this is another property of finite element methods. The stiffness matrix will always be singular. How do we make it non-singular? Well, we applied, even though we haven't written the right-hand side out yet, we applied the Neumann boundary condition. We put P in those equations, right? But we have another boundary condition. What is it?
Bridging.
Huh?
Bridging.
At what end in our problem?
Yes.
Right? U 0 equals 0, okay? So, remember, this matrix here represents a system of equations, right? And so, if I wrote out the system of equations, Oh, what is that? Gosh. Okay. I don't know what's going on. There we go. All right. If I wrote out the system of equations, I would have AE equal to L U1 minus AE over L times U2 equal to 0, and AE L U1 minus plus AE over L U2 is equal to P. And what I want, U1 has to equal to 0, right? So what I want this first equation to read is U1 equal to 0. How do I do that? No, U1 doesn't equal U2. That would be both 0, right? So what we want is U1 to equal 0, right? One way I can enforce that is if I change the first row to put a 1 on the diagonal and 0 out the rest of the row, right? Basically, what I'm saying there is I'm saying this is 1 and this is 0. And if I get that, then the first equation reads U1 equal to 0. Okay? So this is how you can apply the central boundary conditions and make the matrix non-singular, right? So what I can do is go back over here, and I can basically then say that, well, if I say that K, well, I'll say K1, the first row of K, equals 1, 0. Then if I look at what K is, I have that. And then if I take the determinant of K, it's not singular anymore, okay? So let's finally then write our system of equations. We're going to write linear solve K, and then the right-hand side is the vector 0P. So that means that the first U1 is 0 and U2 is what? PL over EA. Got the analytic solution, right? Got it exact. Hmm?
EA is this area of the thing.
EA is the Young's modulus. A is the cross sectional area, but in this case, the cross sectional area is uniform, right? We can make a non-uniform cross sectional area if you want. For example, we could write going back up here. I'll write EY is equal to A0 times 1 minus X over L. So that's a perfectly like conic section where A0 is the right-hand side, right? So you have an initial A0, and then it goes down to a point such that at X equal to L, there's no area, right? So it's like this. So this is A0 this is L, right? So given that setup, going back over here, then I just have to reevaluate the integral. Okay. Apply my boundary condition. Solve the problem. And you know, the other thing is, right, this, all right, this is U, right? But these are the unknown nodal displacements, but remember not dot U, but rather times U. Oh no, that's right. Yeah. So I'll call these are the nodal values, the UJs, right? So my full solution, right? This is a key difference between the finite element method, finite volume, finite difference methods. In finite volume, finite difference methods, you basically you discretize, say, the finite volume method, and you guys all know about at least a little bit about this if you've had reservoir simulation, right? In a finite volume method, everything in the cell is one value, right? You solve for the value of the cell, the pressure in the cell. Well, in a reservoir, the one cell might be 1 kilometer squared, right? So like the pressure is same everywhere, right? But here you have a function, so you can even plot the function, right? So you could plot U of H on the range. Well, we'd have to plug in values, I guess. So for an initial A0 of we'll say a half, and L equal to 1, and EY equal to, well, just 1 for the example. Oh, I need a P also. P is equal to 1. Yeah. So I get a linear displacement field over the solution of this. We could also use a quadratic interpolant, right? So going back up here, if I change the interpolant to quadratic, so second order, right? Now my shape functions look like that, right? I have an interior node, okay? And then my stiffness matrix looks like that, right? And then I need to add another 0 there, and I need to basically say 0, 0 P there, and then that's the displacement field I get if I use a quadratic interpolant. So I get better, right? Get a better interpolant. And so, it wouldn't, so what the previous result was saying was that, even though my section is conic going down to 0, that the displacement field across the length of it was linear. But we know that can't be true, because if it's a uniform displacement, the displacement field is linear, right? So if you're making the cross section smaller as you get towards the end, then it's resistant. If the cross section is getting smaller, its resistance to deforming is going down, right? Because you have less section modulus to resist the deformation, right? Same force, right? Think about what the stress is, right? So if you have a conic section, the stress is increasing as you go across the end because you have a uniform force at the end, P, right? P divided by area, right? So the stress is getting higher as you go towards the end. Therefore, the displacement should go up as you go towards the end. And let's just do one with a cubic. Just because it's all coded up. There's a stiffness matrix. So, are there any questions? I think got through that a little faster than I thought I would, the live coding. I usually I make mistakes and it takes me longer to do the live coding. So I got through that a little faster, so I guess if there are no questions, we'll dismiss a little early today just because what I have next is going to take longer than 10 minutes or so to get through, so I'll just wait until next time. But by the end of the next class, so basically the next thing is to look at how we assemble these matrix equations if we have more than one element, right? So far, everything we've done, we just had one element. And now we'll look how, if we basically have multiple elements, how we assemble these matrix equations into a global stiffness matrix across the whole system, and then from there. So basically, by the end of next class, we'll finish up the 1D finite element method, right? And with a summary in the end, basically just saying this one model problem that we've looked at can describe lots of physics, right? It can describe elasticity in a bar. It can describe heat conduction. It can steady state heat conduction. It can describe steady state pressure diffusion. It's all the same physics, right? I'm sorry. Depending on the choice of the coefficients A, C, and F, if you apply those to the different physics, then this one method that we've described here will solve all of those problems. Okay. Yep.
In which situation would we want to pick the test functions and the shape functions?
Until you have a reason otherwise, you always do. Yeah. So this is the standard Galerkin approximation. You would always do it. And I mean, this is like 90% of all finite element methods, finite element codes. And remember, like every airplane, every car, modern airplane, they're all designed with finite element codes. Like Abacus, ANSYS, Nastran, and then of course there's a ton of open source codes or tools to write codes, frameworks. I'll go over some of those before the end of the class, hopefully. In all of those, the standard approach is to use linear Lagrange Galerkin approximation. So basically just what we covered right here. And that's the way probably 95% of every car, airplane, bridge, everything that we design these days is, so there's like, and all this stuff was really well established by the mid-'80s. Like nothing I taught you today was not like really well established by even the 70s, right? There's one aspect with how we integrate the shape functions, particularly in higher dimensions, that kind of came around in the late 70s. Everything I showed you today was around even before the 60s probably, and yet there's been probably 5 million papers published on finite elements since the mid 60s, and yet every airplane and car and bridge that we design today is still done this way. So all those 5 million papers, I just wrote a bunch of gibberish that no one uses. I'm being a little facetious, right? I mean, again, there are certain cases, like I was saying, like if you really want to design a method that has like a known optical convergence in whatever norm you want, then that would be a situation where you might use a Petrov-Galerkin method where the test functions and the trial functions are different. And you basically use the theory to design the test function so that you get optimal convergence. Yeah, but for the most part, everything is done this way, and it's robust. It works well. Obviously, like anything, there's some gotchas that we'll talk about along the way. There's things to look out for, but for the most part, this is the way it's done.